Good morning, everyone, and welcome to today's IvS seminar. Today we've got Nick, who will be giving a talk about his work in his PhD program. Nick first started his bachelor and master at Aarhus University in Denmark, spent a little bit of time on La Palma as a student astronomer, and now moved to KU Leuven for his PhD. Thank you very much.
Okay, thank you. Thank you for coming to my seminar on the topic of MOCKA simulations for ESA's PLATO space mission, and thanks for the very nice introduction as well. So I will continue to work the line of work that I sort of did a little bit on La Palma, thinking about observations, but this time through simulations. So I'm going to give you a small overview of what we are dealing with here for the PLATO mission. What is it really? Why do we need simulations for PLATO, or for any space mission in that regard? And also, what can we use to understand these simulations? So I use MOCKA simulations for this. And I'm going to show you some applications to both the mission preparation and also to what we call the complementary science program of this overall space mission. But I give you a small introduction to PLATO in the context of what is the real science goal of this mission. So let's jump into it. So this beauty you see on the left here, PLATO, is going to be launched in around 2 to 3 years in December 2026. And the main goal of PLATO is to detect another Earth-like planet around another Sun-like star. This is actually a continuation of what the other space mission prior to this was called Kepler was trying to do. It was trying to find exactly one of these Earth-Sun analogs. Unfortunately, it didn't do so, but it did detect a lot of exoplanets. So what you're seeing here on the right is basically a bulk of planets in this period versus radius diagram. And since you have thousands of planets that have been detected by the transit method using photometry of the Kepler Space Telescope. Unfortunately, there was no Earth-like planet in this sample. And one of the reasons might be that if we look towards the lower corner here of the plot, we don't really have these long period rocky-sized planets, and Kepler sort of failed maybe due to the stars that it was observing. So it was really observing very faint stars, and doing follow-up observations of these and confirm them are quite difficult when they're really faint. So the main methodology for PLATO is slightly different, very similar though, but slightly different. So you might recall back to if you want to detect an exoplanet, you would go typically and survey a lot of stars with a space photometer. You can really get down to the parts per million level, or parts per thousand, depends on how accurate you go. Let's say PLATO will go per parts per million, and you get your transit dips of these exoplanets when they're going in front of the star and transit them. What you really get is actually only the radius of the planet over the radius of the star. And so we need other methods to really gain the knowledge, what is the bulk parameters of our stars. So in this case, PLATO is actually going to use asteroseismology as a dedicated tool to get all of these parameters of the stars, so we can get a very accurate measurement of the radius of the planet. And just to highlight, maybe this is a small commercial for what we're going to do here at this institute. We can take, for example, the beautiful telescope of Marvel. Well, the Marvel survey is 4 telescopes that's going to be built on La Palma, currently being built. And we're going to use quite a lot of time to survey some of these stars to follow up, to see if the planets have these beautiful radial velocity curves, and we can measure the semi-meter amplitude of these stars and get actually a mass of the planets as well. So the main difference, to be honest, is really that we are trying to not only detect, but to characterize exoplanet systems with PLATO compared to Kepler. Great. How does it look like then? Well, PLATO is a sort of a slightly more complex space photometer because it consists of 26 cameras on an optical bench, whereas Kepler, for example, was one big telescope with one big mirror. In this case, we have 26 cameras, and we have opened the angle of each of these small groups of cameras. You can see here, there's like 4 major groups, which we call normal cameras. There's one big group up here, well, of 2 telescopes, which we call fast cameras. So the fast camera is going to be used for the really keep the stability of the spacecraft pointing in one direction, whereas the other telescopes here are mainly going to be used for the science we're going to do. And so the opening angle here you're looking at is sort of projected onto the sky. You can see that they're slightly offset, and they give you this quite complex field of view, effective field of view. So here we have an effective field of view more than 2,000 square degrees, which is huge. It's almost 18 times what we had for Kepler. And the reason we're doing this is because, well, we're going much brighter, and we still want to keep the same amount of solar-like stars, so we need to go much bigger as well. But what you really see here is that you're going to see in the future quite complicated diagrams like this, where you might have a star in the center here, and you have then 24 cameras observing continuously on this target throughout the mission. But then you also might have targets that only have 18, 12, or 6 cameras, and so on. And of course, this is important because prior to your observations, your applications, you want to know what is the noise budget for this specific target, or this cluster, or this binary star, whatever. So it's very important to know this, and you do this in priority. Okay, but I told you just the field of view. Which stars are we going to monitor with PLATO? Well, PLATO is going to look at 2 different fields in the original mission. One is going to be in the south, in galactic coordinates here, you have the galactic plane, and one is going to be towards the original field of the Kepler mission. 2 years, well, it's not much longer than, it's not longer than what Kepler did, of course, but we still have good evidence that we can go and find these exoplanets, still with 2 transits. What you see furthermore is that these fields here, they consist, of course, of some sample of stars, and as I just told you, the mission is targeting solar-like stars, so they're really like in the range of the F5 to K7 spectrotype, and there will be some M-dwarfs in there as well. Well, the exciting part is that I think for most of the people in this room, we have a complementary science program. So actually 8% of the mission operation is dedicated to complementary science, so that means anything outside the exoplanet sciences, and also anything outside the asteroseismology of solar-like stars. So really you can go and you can make your own proposals and get some time in the future for PLATO. So that's really nice. What data projects do you get for PLATO? Well, first of all, one of the data projects you might remember if you were using Kepler data is what we call target pixel files. This is very similar. It's just a small cutout of the detector around your favorite target. There might be the target here and some stellar contaminants you also see there. And you can then extract your photometry however you like. Well, for most of these data projects, if you look at the primary sample, this is around 10,000 stars that are dedicated for PLATO. You will actually download these images to ground, and we can do, for example, some more fancy PSF photometry on this data. But actually, what is quite important, also why we need simulations, is the most of the operations, the most of the light curves we're going to extract is going to be on board the spacecraft. So that puts really, really high constraints on the algorithms you're going to have on your spacecraft. And it also makes it far more complicated in the sense that we only get light curves, so we have no idea if something is wrong, if the systematics might be affecting your data, or there might be other things in your data you don't really know about. So we have to test this in advance, and so a typical light curve for PLATO can look something like this. And well, what you see here every 14 days is simply some mask update. So you take your binary mask, you might reevaluate, is there a better choice for my photometry in this point in time? And you might deselect this pixel to this pixel, and this gives you these flux jumps. This is really just to show the worst case scenario. We're not probably going to do this strategy here, but the light curve, what you get for one single camera, will look something like this for 90 days. And then remember, after 19 days, we will have to rotate our spacecraft around the roll axis, because we need to realign the solar panels to power the whole spacecraft. Because our spacecraft here, like Kepler, is also in the second Lagrange point, so exactly 1 year of the orbit. All right, so the need for simulation is pretty clear from the point of view that we have a lot of data products going to be processed on board. We need to really look at that. That's very important. But there's also some complications. If you think about Kepler, it was quite a small, what we call plate scale. What plate scale essentially is just how well you sample your PSF over your pixel grid. PLATO is quite a small plate scale, so that means that we only have very few pixels to define actually a star, a point source. And so if you look at a simulation like this that I simulated for 90 days, you have the target star, you have multiple contaminants, and this really gets complicated if you also have these stars being variable, right? So we need to disentangle both instrumental systematics towards what we also see in our variable signals. So we need simulations. I hope I convinced you that so far. Okay, so to perform my simulations, we use a tool called PlatoSim, which actually have a heritage here from the Institute. It's really old. It's been developed from multiple missions, and I'm far not the probably the best user to talk about PlatoSim in an essence where it really comes from and how it was developed. But I'm a prime user of PlatoSim as it's part of my PhD. So PlatoSim, I'm going to give an introduction here, what PlatoSim is. But essentially what you think is just that, imagine one of those cameras on the optical bench. What we're trying to do, we're trying to model that. That's it. So really, as efficient we can, we're trying to model one single camera. And so a camera, if you want to put that to scale next to me, I'm pretty tiny, so you, it's quite big. But it looks like this. So in a nutshell, PlatoSim, you can imagine that you have the whole camera with all the optical elements inside it, and at the bottom we have sort of all the detectors in an array we call the focal plane array. This diagram looks sort of like complicated, but what I want to have you to take away is that we simply in the focal plane array have 4 CCDs for every single camera. So that makes the processing and the data amount we get from these cameras huge. And this is one of the reasons that we cannot just download all the images on board. We really need to select our targets, put small pixel frames around them, and for most of the targets we need to just get data points. If you are a user of PlatoSim, what you typically will see is that you will select, depending on what you actually want to simulate, you want to select a piece of the CCD, because simulating a full CCD can take quite a while. It's pretty complicated to do that as well. So you want to maybe simulate just a small subfield, or you want to simulate this main data product, which we call an imagejet. And so for most of my purposes, I'm going to show you some full frame images, but I'm also going to show you the simulation we really do just with the main data product. And the reason is, well, imagine we have to, for one single simulation of 90 days, it's more than 300,000 exposures. That gets quite time-consuming overall. Okay, I will take some water. Okay, so what is the difficulty of creating a pixel simulator in the first place? Well, if you look at the very simple formula for, imagine you just have one single pixel now in the column and row ij, and you have an incoming photoelectrons that you are detecting in your detectors. You can then apply all the gains, you can put all of the bias, the read noise of your CCDs, but the difficulty actually comes from how we would define which is a time step small enough when we can say that an effect should occur and when it should not occur. So this is actually part of the job of PlatoSim to do this. So what we have done is that we split up, for example, the exposure into whatever is happening in the exposure time and whatever happens in the readout time. And we then determine and say, well, what is the heartbeat of PlatoSim? What is the fastest varying time phenomenon that you can think of? And typically, for many simulations, that is the jitter of the spacecraft. So basically, as the movement of the spacecraft tries to just point stable at one point, well, it's not perfect. So we need to track that small movement of the spacecraft that also basically moves around all the stars in the focal plane. So we do this here. We take a very small time step, and then we make an assumption that everything in our readout is sort of can be averaged. And the reason we do this is I will explain a bit later. Another issue, of course, is that, well, we also have to consider that every single pixel also has a wavelength dependence. And how do we get rid of that? Well, we can make averages of all of the quantities, so all the incoming light from the star, the sky, the stray light, and for example, all the different optical elements, the detectors, how efficient they are, we can also try to make some averages. And this is one of, let's say, it's a shortcut that's done for PlatoSim to make it fast. But of course, other simulators, like for example, take the KIRPS mission, has a simulator that can simulate very small subfields for exoplanets, but take the wavelength dependence into account. So it's just it's a trade-off you sort of have to make. So let's look at some of these parameters that we have of the incoming light, both from the star, and also look at some of these parameters. We define how much of the light is going through our instrument, how efficient our instrument actually. So first, you probably have all seen a point spread function before, but maybe not as funky as this, or maybe you have, I don't know. But essentially what you're seeing here is a CMAX model, so this program, ray tracing program CMAX, that can create really accurate estimates of how the point spread function will look in high resolution. We use this to basically imprint into our data before we then overlay the pixel. And then we take into account all the different effects that might happen as well over time, of course, the small time step. So what you see here is that, remember that we're having like at one telescope, and so along the optical axis, the PSF might be very like Gaussian-ish or very narrow, and then you move further out in the field of view, and you really start to see some very elongated PSFs. If we take into account that we have in the detector itself that charge might diffuse from one pixel to the other, you get like sort of a blurring effect. And sort of this is actually the more realistic effect you're going to be seeing. This is the optical system as a whole, but this is the detector level, what you're seeing. I mentioned before just the PSF, how it looks so different when you are close to the optical axis here. So this is, remember, one CCD. You have another CCD here and down as well. So this is the optical axis of your camera. And if you go out, of course, you have also a decrease in your transmission efficiency, simply due to that we are working with refractive elements, and they are just slightly better here in the center. We also have detector effects, such as we need to know how efficient the CCD is. The pixel might be slightly different in their sensitivity, so this is also something we take into account. And very lastly, before I would go to some more exciting news, here we have the very last component. I mentioned that in the readout, we take the average of a lot of the parameters, and the reason is that we kind of model these effects as they are electrons redistributed on the surface of a CCD or in the substrate of a CCD. So one classical effect I would like to highlight is, for example, if you remember back many years ago now, the first really robust algorithms to model what we call the charge transfer inefficiency was actually done for the Hubble Space Telescope. And the reason we start to notice these effects is because we move to space, where the environment of your cosmic rays are really bombarding your CCDs and destroying the substrate. So if you remember back to your solid state physics, that create electron hole pairs. And during a readout, we might capture some of these electrons that actually are part of the readout procedure. And then they're released at a later time. And what you get back in your image is sort of these beautiful trails, which is very annoying for science. So we need an algorithm for that, but we take that into account as well. This is just one example of the different effects you can put into your simulator. All right, so mock simulations. If you ever heard about mocking in science, that's probably not a good thing, but in this case, we use these kind of mock scenarios to have a test environment where we really can make sure that everything we do is controlled. And what I mean by making mock objects is actually making fake stars, so to say. Fake stars and, let's say, fake variability signals that we can inject into our simulations at pixel level, and then we can extract that photometry. So it's really like end-to-end going from the incoming photons to the outgoing signal we have as well. So I use simulations to do this, and I made as basically part of my PhD, I made a setup that I coupled to PlatoSim, which I call Plutonium, which is not a real element, but still. This tool is essentially just to transform PlatoSim into a mission simulator, because remember, PlatoSim was actually only a camera simulator. So we need to be able to simulate all of the 24 cameras in our spacecraft instead of just one. So that's what I've been working quite a lot on doing. And make this realistic in the sense that we have a setup that we can get a distribution of stars, we can inject them, we can run them on our supercomputing cluster, we can get some simulations within human timescales. Because otherwise, doing this from scratch, it takes days to do. So this was part of why I did this. So with this, I'm going to show you some. I'm going to show you some examples in a moment. But just to give you a short tutorial, step by step, what is actually really happening here? Why is this important for the mock simulations? Well, first of all, as I mentioned, if you are interested in a particular star, you want to select, for example, where it might be in the sky. You want to know exactly what the noise levels are. So this is a tool to kind of collect the stars you can simulate and get this distribution. You might as well also inject some variable signals. So we have a tool that does that for you as well, depending on if you are interested in the mission, the core mission science, for example, the solar-like stars for the exoplanet, or if you're more interested in the complementary science, which I will show you in a second. One of the assets of using Plutonium is that it will also create some files for you that can be used directly by PlatoSim for this instrumental systematics. And one of the things that are quite important to take into account is that, well, if you imagine one camera group, you have 6 cameras pointing exactly in the same direction. That's not really realistic because we know that cameras, of course, have a slight offset. So that could be one thing to take into account here. And this is, for example, shown just projected into the pixel space, how that will look like for the 24 cameras and the 2 fast camera for sort of like a random distribution of this. And lastly, of course, we launched the simulation on a supercomputer platform, tracing where all the stars are, which is also can be important for you if you want to in the future know exactly what are you actually dealing with here, which kind of effects should you take into account, and the noise level as well. All right, so let's move to the applications of this tool. Well, maybe before I do, I would maybe introduce, we have a quite large team here at KU Leuven, which is working on PLATO. So, of course, you can see most of them are sitting in the audience here, with Connie and Andrew controlling and managing all the science aspects of the mission, and of course, Connie being the main lead of our team. But with Bart, he's our manager, let's say. Yeah, it's a fancy name. And make sure that everyone is doing the job, which is a good thing. Rick is really a software guy. He's doing crazy stuff on developing tools that can be used in the test houses to set up things and control things. It's really cool. Where Sarah and Pierre, among others, are working on the assembly of all the cameras and the integration and the verification of these things as well. And the rest, Joris, Dries, and myself, we are the sort of like the software developers of PlatoSim. So with that, let's have a look what, from the mission point of view, what can we use PlatoSim for? So one of the things we did actually in the paper when we published PlatoSim was to look what kind of noise level we get as a function of the stellar magnitude we are looking at here. So what I'm showing you here is the noise to signal ratio. It's just the inverse of the signal to noise ratio, okay? And it's the precision you have over an hour of observation. On your x-axis here, you see the magnitude of your stars, right? And what I did, I simulated the entirety of the core sample that's going to be used for PLATO. So we call it the P1 sample, some jargon, but it's just 10,000 stars that are very bright. It's up to around 12, 13 magnitude. And you can kind of see that all the stars that are completely blue here don't have any stellar contaminants, which means that, okay, there's no extra noise from other stellar contaminants in their subfields. But you also do have stars that have some stellar contaminants, and you typically see there's a decrease in the noise, which is not real. It's actually because you're just adding more flux from another star, so you're suppressing the noise here. But so thinking only of this major curve here, you can see that there are sort of 3 scenarios we can be placed in, which is important if you want to go and take a target and you want to know exactly what kind of noise budget you can expect from it. You can kind of take a curve like this and say, well, if we go very faint, we know that the readout noise and the sky background is going to be dominating your systematics, or your noise budget. And if you go a bit brighter, we know that the target itself, the photon noise of the target, is going to be dominating. And even brighter, we know the instrument, the stability of the instrument is going to be the dominant factor here. We actually don't really we don't reach for the normal cameras, the 24 normal cameras. We don't reach this limit of where the jitter is going to be the very dominating source. Because what happens here is that we start to have saturation. So we're basically filling up every pixel with all the electrons we can. And then we start to actually spill flux out of the small 6x6 subfields. So here you just see scatter, essentially. Of course, these simulations were done for the real stars we're going to be doing in the future, so they had the real distribution over the sky. So we can also look at it from the point of view of the instrument level, or the mission level, let's say. So taking all these observations now, gathering together what is the noise level if we then combine with how many cameras they have. And what you see is essentially the same. But the main thing we want to really test here was this requirement you see here, which is a big vertical line. So we know that one of the requirements of the mission to detect an Earth-sized planet in 1 year orbit around a sun-like star is to have a noise-to-signal ratio lower than 50 parts per million in 1 hour observations for a star that is brighter than 11 magnitude. So that's pretty good. We did that We showed that with simulations, which of course we hoped with the whole design that would work. So that's good. Another project that was involved in the mission was to look at how we could, in the best way, and also what kind of rates we will get for compressing the data on board the spacecraft, send it down to ground, and then unpack it again. And this is quite an important aspect, because if this fails, everything fails. So to give it a bit more a spice to it, we also made, instead of making small subfields, we made full-frame images, so it could be used for other people in the consortium as well. So this is sort of the first slide you will see probably of what it will look like in the future for PLATO, for a direction of the Large Magellanic Cloud here. And you have a small bit zoom in, so just to show the scale of how big the field of view is for PLATO. So, all right, I'm going to skip the core science applications, but essentially what I think you can take away is that with the requirement we proved before, we did the same test for like really trying to look at what if we try to inject an Earth-like planet around a Sun-like star in 1 year orbit. Can we do that? And sure, that turns out to be really fine. We can detect it easily with 2 transits. So I'm not going to show you that. I have the slide if you want to know more, but I'm going to venture a bit more into the complementary science. All right. So some applications to this complementary science program. I can first ask, what is this program actually about? Well, you might see here that it's part of the mission strategy to have these 8% of the time dedicated to a guest observer program. So that means you can apply for the time and you might get it, but you also might want to have a good application to put in and say that I know with some simulations that my science can actually be achieved with this spacecraft. That would be a very good thing to do, for example. So you have Connie and Andrew being the managers or the coordinators and manager here of this program. And what you see here is that Andrew is sort of the overall coordinator between all of these, what we call work packages. So this overall work package that's designed to get the best yield of each of these sciences. What I will focus on, is the package of pulsating stars, because it's quite relevant for our institute and our group here, and quite an exciting topic to work with as well. So, the first project I want to present, which is still ongoing, so I have only preliminary results, is a catalog we are trying to create called MOCKA, which is a PLATO asteroseismic model catalog. This catalog is essentially set out to simulate all the different types of pulsating stars that we have of intermediate to high mass stars, and we want to know if we can retrieve the important pulsation modes that we use for asteroseismic modeling. So what we did as the first glance here is to go, now show the same plot as I showed in the beginning. This is actually from this paper in preparation of this MOCKA catalog, where we queried all the Gaia stars up to 18 magnitude in the field of view of the south Plato field. And we're going to use these stars to have realistic distribution of the different stellar pulsations, pulsation classes, instead of just using some kind of made-up catalog. If we take all the stars that are within 1 kiloparsec in this big field of view, what you see, you get this beautiful main sequence here, and subgiant branch, red giant branch, and so on. And so, of course, this diagram is the color absolute magnitude diagram in the Gaia bandpass, as you might have noticed. But you recognize probably a lot of these different branches of stellar evolution. But what I want to highlight is just that we are really going for the intermediate to more massive stars and analyzing those to see if we can retract or get the frequencies out and the pulsation modes. So the first thing I'm doing now is looking into the specifics of Gamma Dorado stars. So analyzing this whole sample is quite a big mouthful, so I'm just starting with these specific stars. And the reason why we are specifically targeting Gamma Dorado stars is because they're quite unique in the sense of what kind of science we can get out and what we can use them for. So if you don't know them, these stars, they are like early to late A-type stars. That means that masses in between 1.2 to 2 solar masses, and they have convective cores and a convective envelope that are slowly disappearing as far if you go up in mass as well. The pulsations of these stars is from gravity modes, and they are non-radial, so that means that we can really learn something about how they trace near the core. They're very sensitive to the physics that happens near the core of these stars. And that's pretty cool, because then we can start to think about what happened in the interface between the convective core, the radiative envelope, or the radiative outer boundary here. And also, for example, ask some questions about what is the angular momentum transport, what is the mixing, can we rejuvenate these stars by different mixing procedures, and so on. So they're quite interesting, and they can therefore also be used for calibrators of stellar models. So we start with these ones. What we are doing now is, well, what I already did was to simulate a lot of mock objects or mock light curves, which looks sort of like this. And the way we get there is to use real simulations, or real observations, sorry, of a Kepler sample from Gang Li and collaborators 2020. And from that distribution, we can sort of recreate, from the amplitude spectrum, we can recreate our light curves. So we get something that looks like this. So that's what we're going to inject in our simulations. The point of these simulations is to test. I already mentioned in the beginning that the difficulties in making observations and then interpreting your result, of course, is typically depending on your instrumental systematics and how much stellar contamination you have and what kind of stellar variability is contaminating your star. So what we're really trying to answer here is to take a set of simulations where we just have everything as expected. We don't have too much instrumental systematics. We don't have something that dominates the variable signals for contaminant stars. And then we test it against these two other extremes, which is the instrumental systematics being completely dominated in the simulations, and where we have the stellar contaminations, the variable signals of contaminant stars being dominated. So far, the first simulations I have made, they're done now, and I'm starting to run basically these two extreme cases. But so the first very simple case here, which is let's say the nominal simulations, are done and needs to be analyzed now. But it's, of course, it looks as expected, more or less. So what we have in this diagram is that you see all the orange dots here is what we inject as pulsation modes in our star. That's what it looks like. And then we use the code of actually Luke to retrieve all the modes in our light curves after we have pushed it through our entire simulation chain with PlatoSim and everything. And that's what you see in blue together with the pink circles here. So if you zoom in on the region of interest, sort of the area where we can form so-called period spacing patterns, these are like characteristic patterns of G-mode pulsators. We want to find out if we can create these patterns or recreate such patterns and learn something about the physics of these stars. So for now, it looks pretty fine. If you look at the residuals of the frequencies that we can extract, we might miss some frequencies just due to the detection, but that's pretty normal. But overall, it looks like what we expect from a star of this magnitude and of the noise level we have injected. So this is pretty fine. We will see for the future what will come up. The last project I want to talk about is a bit more extreme, let's say. It's going completely in the far end of the box of complementary science, because we are looking at very exotic objects called supermassive black hole binaries. And so these objects, which is illustrated really nicely with this simulation by NASA, is sort of the idea of having two supermassive black hole binaries with each increasing disk. And when they are with the right angle, just like with the transit method, when they are eclipsing each other, you see these like warping effects of the increasing disk of the other supermassive black hole. So it looks pretty cool, but of course that gives really like some intrinsic variability into your light curves, and you can go and see, maybe you can hunt them down, you can learn something about the binarity of these objects, and potentially the merger of them that will lead to gravitational waves as well in the future. So this was a project that was initiated when Jordi Devalar last year was visiting, and it's a very fun project to continue down this road. So what is actually, so from the theoretical background, why do we think that this is actually important? Well, we know that these objects, at least from theoretical point of view, should exist if we just take the classical galaxy merger model of how galaxies are formed and how black holes are formed. So we expect that in the earlier universe, we will have already supermassive black hole formed in these axial galaxy nuclei. So this is also what in the future we can go maybe and look for in the Gaia catalog, and then find out, is there any of these that are potentials for putting in an application for PLATO to observe. from an observational point of view, I'm also going to show you an example of actually one we did observe with Kepler. So there is also an observational background, let's say, or a sediment for doing this. All right, feasible with PLATO. That was a question I sort of we asked. And initially, what we just really vaguely did was to say, okay, let's first see, can we even detect these things? They're really, really faint. PLATO is designed to observe very bright stars. So is this even possible? And just to make it fast, I made just some very simple toy model of what we call the self-lensing effect here. So that's when the two black holes are going in front of each other and then warp the entire disk of the other black hole. And then we also have the effect of what we call Doppler boosting, essentially just the enhancements of the light while you have the relativistic speeds of these two objects while they orbit each other, which is typically imprinted as like a sinusoidal signal here. So those two together, we just looked how faint can we go, which configuration. So this was just one simple example of 1,000 targets we injected with different kind of parameters. And very well, it looks pretty promising, but of course this is very optimistic. And this is, for many of them, was quite bright as well. So what we need to do, the next steps, is to, of course, we need to get a better model of the lensing effect, the Doppler boosting as well. And what we haven't included in our model here is actually one of the probably most important ones, because they add noise to our light curve, and that's the quasar variability. While material of the surrounding increasing this or falling into the black hole, that rate of increasing is not constant, right? So we need to make that more realistic. So this is the observational evidence that we might have observed a supermassive black hole binary in quite an eccentric orbit here. This was done by Hugh and collaborators in 2020. And what you basically see is that the data points in black is what Kepler observed. You can't really see them here on the lensing effect, but it looks pretty convincing to me that this might be one of these objects, and also by Gaia characterized as one of the AGNs in the field view. So what we need now is to not only do a model like these guys did, but we need to expand it with this quasar variability, because we are not trying to only model a light curve. We're trying to make the light curve and then model it. So we are doing an extra step in this sense. And I had quite a successful student project with some bright students that took the model of this paper and got all the three components. The quasar variability is they simply used a red noise model as like a random damped walk. And they get pretty convincing light curve out of this, which I simulated for them. So there might be some parameters that need to be tuned, or some things that doesn't look completely right. But I think we're on the right track here, and I think it's quite fun to see how we compare to Kepler and how we do with PLATO. So the future of this project would be to do more or less the same as we did before, now expanding the parameter space more, getting more realistic effects of the relativistic effects of the self-lensing effect and everything else. And hopefully then with collaboration with Pablo, we can maybe use machine learning algorithms to see how efficiently we can detect these things. Can we retrieve these signals actually? There might only be 1 or 2 or 10 in our PLATO data, but it could still be fun to try to look for them, I think. So, okay. And very lastly, this is my summary slide, a bit early on time. So, but more questions, I guess. And I think I would rather have you read this instead. I want to just convey 2 main messages. So first of all, I hope that I convinced you that running simulations for the preparation of any mission, not only a space mission, is quite important. In this case, it's really like an asset to understand the underlying systematics and the stellar contamination. Hopefully, I will be able to show more results very soon on this aspect. And yeah, I hope that you would like mock simulation in the future as well. That's basically it. Thank you.
Thanks, Nick, for a very interesting talk. Are there any questions?
Thanks, that was a great talk. I was just wondering, on your quasar variability, you got 2 black holes. how many quasars do you have? Like, do you want, like, is the idea, is it 2 quasars orbiting each other? And if so, would the idea then to have a superposition of 2 quasar variability terms, which in which case you might get, for example, spikes where they agree, and then like a more spiky distribution, I imagine, would be the net effect?
Yeah. I think I forgot to mention that, but I think from my understanding, the 2 like so much black hole binaries only kind of exist when the galaxies of 2 large galaxies merge, right? So it's not 2 AGNs. It's sort of a phase in time where you have 2 galaxies that have already merged, and then they form sort of like one AGN as such.
Okay, so you do expect just one of them to act like a quasar then, and the other one to be closer to a negative?
I think it really depends on the masses, right? But I guess in most cases, there would be one of them that would be dominating the mass completely.
Yeah, probably. Okay, thanks.
Hello, I have a question. So at the beginning of your talk, you mentioned that PLATO will be more interested in the cool stars. So my question is, if the PLATO is suitable for like gamma dose stars or SPP stars, which is early type stars. Thank you.
So the question is if these will be part of the core science program, the gamma dwarf stars.
Yeah, and how much time will PLATO spend on the early type stars?
On the complementary science, you mean?
Sorry? Yeah,
on the complementary science.
Sorry?
Yeah, so the complementary science is the 8%, so it really depends on how much you're willing to put in your guest observer proposals, I think. But as part of like the activities that's done here at the Institute, we do already have like a small sample which is going to be used for the calibration of stars, and those include gamma Dorado stars as well. So there is already reserved, you can say, time for some of these intermediate mass pulsating stars.
Okay,
yeah.
Thank you.
2000, Connie says, yeah. I couldn't remember off the top of my head, so.
Thanks, Nick. I think I understood that PLATO was meant to observe Earth-like planets around Sun-like stars. So you expect a transit once a year then? So after how many transit or after how many years can you confirm an Earth-like exoplanet?
Oh, you're hitting PLATO where it hurts. It's true. So, I mean, typically you would say you need 3 transits, right? So the third transit is kind of the dead-on confirmation that this is a repeating signal. For PLATO, if you have a 1-year orbit, yeah, you can get up to 3, right? But you typically also get 2 transits. So I think there's going to be drawn a lot of information from the knowledge of what we're actually doing now for exoplanet science, of transit detection, of monotransit, double transits, and so on. But just the fact that we get the candidate is also quite important, right? So in this case, what I showed in the simulations, I even think I can. So this was the simulations that I did for the PlatoSim paper, where we just showed this exactly, where I exactly took your example. I would be like, but wait, shouldn't there be maybe 3 transits? So what I did, I tried to test it against having 1, 2, 3, or 4 transits, because the mission was only designed to look 2 years, but wouldn't maybe be better to look 4 years like Kepler did? So that was quite an important question. So in all cases, what I showed, just running the nominal simulations and the instrumental systematics we have, is that even with the 2 transits, you can retrieve the signal detection efficiency higher than whatever is a threshold. In this case, it's a threshold of 9, which typically means that 1 out of 10,000 planets is a false positive. So it was, yeah, it was pretty okay. So I would say, like, for the candidate selection, it's still okay, because in any case, many of these candidates, you will be going through the whole network of PLATO, which also incorporates a whole radio velocity follow-up program. And there you will be able to say, okay, is this really a planet or not? And okay, you might waste a little bit of time, I guess, but for most cases,
So you just announced us right now that 2028 first Earth-like exoplanets detected. Okay. I note that information.
Let's hope so.
Thank you.
In a great talk. I had a similar question. It's about, you mentioned with asteroseismology, you'll be measuring some of the parameters, but one of the things I know is that the longer the time base or the longer the time curve, the light curve, the smaller the uncertainties on these parameters.
Yeah.
So how exactly do you handle this need to observe a certain target for long enough to get the uncertainty small enough to meet the goals of the mission? Do you have an idea per stellar
so
type? Or,
if you only think about the solar-like stars, where we expect to have, for example, radius of 3%, mass of 5%, and ages of 10% or something like that, the compensation in how bright the targets are compared to Kepler is really what is making the difference here. So you have the 2-year time base, for sure. It would be better with 4 years, for sure. But within the, let's say, the requirement of the mission, we are here to those requirements. So it's literally just because we also have bright stars that we can monitor and get much more precise asteroseismology.
So will you wait for those 2 years to lapse in order to determine? I guess not, right? The parameters you will already get.
I mean, you
smaller uncertainties over time.
I'm pretty sure that papers will be published only with a few mission quarters. But I'm pretty sure, like, of course, after 2 years, and let's say that ESA decides to say, now we go for the north pointing field.
Yeah.
Then sure, that will be the end of that until you might return once again if you have an extended mission. But
okay, that makes sense. Right. Thanks.
At least that's what I think for the Kepler. A lot of people they had to publish, right? So they had to make an estimate what the data they had, and then later on they could include more data, get even more precise measurement. And
that makes sense.
Yeah.
Thanks.
Are there any other questions?
Another question, just a remark for you two. So we will already apply for a mission prolongation before the mission is launched, actually. Because the majority of the people in the science team actually want to stay on the field for 4 years, but we can't for political, financial reasons, which is ridiculous, but that's the way ESA works. So that's one thing. And secondly, the radial velocity follow-up is an integral part of the mission, which is something that ESA has to learn how to deal with, because it's ground-based photometry. This is all sorts of astropolitics. You cannot imagine how it works. But because of that, 1 transit might be enough. If you have a big, large telescope for a long time, okay? Or a few small telescopes that work together and then hopefully are in the correct hemisphere.
By any chance on La Palma as well?
It's easier to point a satellite than to move a telescope.
Are there any other questions or comments? I think in that case we can thank Nick again for his talk. Thank you all for coming and see you next week.